Welcome back to section 7 of chapter 9. This is our last section. How exciting is that? Um, and for the last section, we're going to be looking at two-dimensional motion. Most of the time, we've been looking at motion. It's always been single dimension. It's always been the particle traveling along the x-axis, going back and forth. Really quite boring. And that's not really what things do. Things go up in the air and they come back down. It could be 3 dimensions, but a lot of times things tend to move in 2 dimensions, and it's just the plane might not be on the ground. It'll be vertical, with the x direction being horizontal and the y direction being vertical. Um, and so we're going to be able to see things. We'll be using gravity, all sorts of stuff like that, and it gets you started to get into a 3 dimensional space and movement, which we won't quite get to this year. Um, but 2 dimensional motion's fun. A lot of the stuff you're going to see, and it's going to be familiar because we've dealt with this type of stuff before. You've dealt with it in physics. This is going to be some of the math behind why it happens. And we'll be using vector functions to do it, because as we saw last section, vector functions can be very useful in describing motion and real world stuff, because it doesn't have to be a function. It can do all sorts of crazy things, but it could be a function. It's parametric, so it splits into the x and y components naturally, and allows us to do stuff like that. So it's all fun and games. So the first thing we're going to look at is the position, velocity, speed, acceleration. We've seen this relationship before, and honestly, in 2 dimensional motion, the relationship is the same. It's not changing. If we start out with our position function, r of t, which is just x of t comma y of t, it's our vector, and we want the velocity. Now the velocity on the graph, it's going to always be going in whatever direction the position is going in at that time. So at this first one, this piece is moving in that direction. The velocity is in that direction. The thing that's curving it is going to be the acceleration. So the velocity is the tangent line to the curve, and that's just the derivative. So the velocity is the derivative of the position function, just like it always has been. The speed is the absolute value of the velocity, but with vectors that doesn't really make that much sense. But what the symbol though is the same. The absolute value of a vector, it's the magnitude, and that's what the speed is. The speed is the magnitude of that vector. Now what's fun about the speed is it's a scalar multiple, so we can just multiply that. It's not a vector like the velocity or the acceleration or the position will be. And it's just that usually we would get the speed at a certain time, but we don't have to. We could get the speed as an equation, which is just the derivative of t squared plus the derivative of x squared plus the derivative of y squared, and then square root. And that could be an equation. It could be a number. It depends on what we have to plug in. Now looking at the acceleration, acceleration is the rate of change of velocity. It's a change in velocity. So in this one, our tangent, it starts out here, and then it's going to be curving that way, which means the acceleration, as we can see, is pulling in that direction each time, and that's what's curving the velocity that direction, which is what curves the position in that direction. And the acceleration is just the derivative of the velocity, which is the second derivative of the position. And remember, for second derivatives, we would just take the derivative of the derivative, just like we would do for a normal function. It's nothing special. And so, a quick recap of just what we saw. position, velocity, speed, acceleration. Position's r of t, velocity is the derivative, the speed is the scalar, and it's the magnitude of the velocity, and the acceleration is the derivative of the velocity, or the second derivative of the position. So let's look at a problem. Consider the two-dimensional motion given by the position vector. R of t is 3 cosine t, comma 3 sine t, for t is between 0 and 2 pi. First, we'd want to sketch the trajectory of the object. The trajectory is just the position. It's the path the object takes. So, if we have our graph, now I look at this 3 cosine t, 3 sine t, and I see, hey, that is a circle with a radius of 3. We're going to see how well I can draw a circle on my computer here. My guess is not very. I was right, not very well at all. But it'll work. So we start there, and I completely did not start at the right place, nor did I go the correct direction when I was doing that. We're starting here, and we're moving around the circle this way. And if you plug in points, you can see that. If you plug in t is 0, you'd have 3 comma 0. And then if you plug in t is 1, or t is pi over 2, you'd have 0 comma 3. And then pi, you'd have negative 3 comma 0, and 3 pi over 2, you'd have 0 comma negative 3. So you can see which direction it's moving around the circle. Then find the velocity and speed of the object. So the velocity is going to be the derivative, v of t. The derivative of 3 cosine t will be negative 3 sine t, comma. The derivative of 3 sine t is 3 cosine t. So that's the velocity, and we can plug in points for any given point. The speed will be the magnitude. It'll be the square root of the first one squared, negative 3 sine t squared, plus 3 cosine t squared, which we can square both of those to get 9 sine squared plus 9 cosine squared. I'm going to factor out a 9 to end up with sine squared t plus cosine squared t. There's that Pythagorean identity just popping up once again. Sine squared t plus cosine squared t equals 1. So this is just square root of 9, which is 3. We're going at a constant speed around the entire time. And then find the acceleration of the object. So the acceleration, so sine will give us cosine, so this will be negative 3 cosine t, comma, then 3 cosine, that'll be negative 3 sine t. And so it's the acceleration, and we can find it again at different points. And then sketch the position, velocity, and acceleration vectors for t equals 0, pi over 2, pi, 3 pi over 2. So the position, we're just on the circle and we're going in the direction it says we're going. The velocity, we can plug in points for this. And what we'll see is at 0, the velocity will be 0 comma 3. So we're going straight up in the air, 3. And then at pi over 2, we'll be going straight horizontal, 3. We'll be going straight down, 3. And straight over 3. So that's the velocity. And the acceleration is kind of fun for a circle because, let's see, I'll go with green. If we notice, we have -3 cosine t, -3 sine t. The original function was 3 cosine t, 3 sine t. That's the radius. The acceleration is the negative radius. A of t equals negative r of t. So the acceleration at any given point on the circle is going back to the center of the circle. Acceleration is it's pulling you into the center of the circle. The thing that keeps it from going into the center is the velocity is constantly taking you away from the center. This is like ellipses work the same way. So like planetary orbits, the sun's gravity is constantly pulling us to inward, but the velocity is such where we keep our orbit the same all year long. Well, with the fluctuations of the ellipse, but it's going to repeat. We're not like slowly, well, not at least noticeably, spiraling in or spiraling away. We're staying in the same relative place. And that's just, I don't know, I find it fascinating. I find it amazing. And here, this is the math behind that. This is what makes it happen. So that's always fun to see. Next one, motion in the plane. So here an object begins moving horizontally from the origin with a velocity v of t. So now we have velocity, not position. V of t equals 2e to the negative t over 10, comma 1 minus 4 over t plus 1, and t is greater than or equal to 0. Assume the x-axis points east and the y-axis points north. So instead of being horizontal and vertical, it's like a map. We're going east and north. At what time is the object moving eastward? So for this case, we want to know when is this x velocity positive. That's when it'll be moving eastward. That's not directly east. It's moving east and maybe north, maybe south, maybe just straight east, but it's moving in the eastward direction. So when is e, or 2e to the negative t over 10 positive? Well, e to the negative t over 10, e to a power is always going to be positive. It's always going to be greater than 0. When we multiply that by 2, it will still always be greater than 0. So at what times is it moving eastward? It's always. So for t is greater than or equal to 0. Technically, if t was less than 0, it would still be moving eastward, but we're not concerned about that because that's not in our domain. At what time is the object moving northward? So for this one, we need the y value to be positive. So for the y value to be positive, that was not supposed to happen. There we go. The y value to be positive, we just need to say 0 is greater than 1 minus 4 over t plus 1. We can subtract, so we get 4 over t plus 1 is greater than 1. Multiply the t plus 1, which will be positive, so we don't have to worry about flipping the sign. T is greater than 0, so t plus 1 will be greater than 0. Also, notice t can't equal negative 1. It's not in the domain. We don't care. But we can multiply the t plus 1 over. So 4 is greater than t plus 1. Subtract. 3 is greater than t. So when t is less than 3, nope, I had that wrong. The sign's backwards. I put it 0 is greater than. It needed to be 0 is less than. What we're looking at has to be greater than 0 because we want to be moving north. We want to be moving up. So when t is greater than 3, we'll be moving up, which means that when t is less than 3, we should be moving down. We should move into the south. And when t equals 3, we should have that 0. in the y-axis, or the x-axis, the y equals 0. So, what time is the object moving northward? T is greater than 3. Find the acceleration of the object and determine when the object accelerates or decelerates in the x and y directions. So, we'll have the acceleration. We need to find the derivatives. Let's get rid of my circles there so we can see what we're doing. So our derivatives, derivative of 2e to the negative t over 10 will be e to the negative t over 10 times negative 1 over 10. So this will be 1/5 times e to the negative t over 10, because 2 over 10 is negative 1/5, and the e to the negative t over 10 stays the same. And then the 1 goes away, so we have negative 4 over t plus 1, so that's t plus 1 to the negative 1, so multiply by negative 1. We get t plus 1 to the negative 2 times the derivative of that, which is just 1, so this will be 4 over t plus 1 squared. And so now we need to see when is the object accelerating or decelerating in the x and y directions. So in the x direction, we know that e to the power is going to be positive. We multiply by 1/5, it's going to be positive. Hit that negative in front, it's going to be negative. So this will decelerate. So x direction will decelerate for t is greater than or equal to 0. And in the y direction, we have t plus 1 is always going to be positive. We square it, it's always going to be positive. 4 divided by a positive number will be positive. So the y acceleration will always be positive. So it'll be accelerating for t is greater than or equal to 0. So it will always be accelerating. So what's interesting here is it's constantly moving east, but it's moving east slower and slower and slower, while it's moving north faster and faster and faster. So that creates a fairly interesting part of the graph. And so let's see, part D, find the position vector for the object when t is greater than or equal to 0. So we have to take the antiderivative. So r of t will have the antiderivative. So the 2e times the negative t over 10, it'll still be e to the negative t over 10. Instead of multiplying by negative 1/10, we'll divide by negative 1/10, which is the same as multiplying by 10. So instead of negative 1/5, we get negative 20 e to the negative t over 10, comma. The 1 becomes a t, and then minus the 4 over t plus 1. We have the over t plus 1, that's going to be a natural log. We don't really need the u because it'll just equal 1. So this will be minus 4 times natural log of t plus 1. Technically, we would want absolute values around the t plus 1. However, t is always greater than 0, so t plus 1 is always greater than 0. So the absolute values are superfluous. And then plus our c. That would be c1, comma c2. And now we can figure out what those c's are going to be and then add them in. It says it starts from the origin, so it'll start from 0, 0. So if we plug in 0, because the time would be 0, we should get 0, 0. So here we get negative 20. E to the 0 is going to be 1, so this is negative 20, comma. Then plug in 0, we get 0. Minus 4 times 0 plus 1. The natural log of 1 is 0, so this is 0 plus C1 comma C2. C2 is okay because that's already 0, but C1 is going to have to be a 20 to counteract that negative 20. So we can plug that back in instead of keeping it separate. C1 will just be a 20, so we'll have 20 minus 20e to the negative t over 10, comma, t minus 4, natural log of t plus 1. And there's our position vector. Then the last step, describe the path of the object and verify your results using a graphing calculator. And so I'm going to get rid of these calculations right up here. So describe the path of the function. What's happening? Well, we know that we're going to be positive in the x direction, mostly positive in the y direction. We're always going to be increasing. At 3, the y value will start increasing, which means it'll be going down before that, which we start at 0, 0. We'll go down, and then we'll go up, increasing more and more. And there will be an asymptote here because as t is getting bigger and bigger and bigger, as that t is getting bigger and bigger and bigger, that's a e to the negative infinity. That's 1 over e to the infinity. That is getting closer and closer to 0. And so r of t is approaching 20. It will never actually cross 20 in the x direction. So there's a vertical asymptote there at 20, which if we graph it in our calculator, we can find that. You might be thinking to yourself, how are we going to graph this in our calculator? Well, you could just plug in a whole bunch of points, which may be the best. It's looking to see like, hey, this is going to be 20. Because I'm looking like, let's see, x is going to equal that. Trying to solve for t is going to be a little bit brutal. So you might just have to go with the descriptions that we have from the other stuff. Checking in your calculator might not be a very good possibility on this one. Extra one case in base. Two-dimensional motion in a gravitational field. Doesn't that sound like it's going to be fun? Honestly, this is what you've been doing with gravity since Algebra 2. You've been doing it in physics. We're going to look at it with vectors, but it's still going to be the same thing. So, gravity, we get to use Newton's second law of motion, which says mass times acceleration equals the sum of all forces. Now, there's a lot of forces that are going to be acting on stuff. We're going to simplify it a little bit. We're going to simplify it and consider only the force of gravity. We're going to do that because it makes the problems much, much easier. And gravity is constant. The other forces, wind resistance, things like that, that's all going to depend on the shape of the item. It's going to depend on the altitude that you're at. It's going to depend on a lot of different things, whereas gravity is going to be relatively consistent. And so we have mass times acceleration equals force, and the force, being that it's only gravity, it's going to be vertical. So we have 0 for x, and then the force of gravity is negative mass times gravity. And if you remember, gravity is going to be 9.8 meters per second squared, or 32 feet per second squared. Depends on what kind of units you're working in. I would imagine probably the 9.8 is going to be more consistent, but you never know. Sometimes I put that as negative 9.8, negative 32, but notice here we already have a negative in our equation. So the gravitational constants can be positive. And so, fun story, if we divide by the mass, the mass cancels. So the acceleration will equal 0, comma, the negative gravity. The acceleration is due only to gravity. It does not matter the mass of the object. Amazing video showing this. The whole, if you drop two things of different weights at the same time, they will land at the same time. A great video where they took the vacuum chamber for NASA, and they dropped a bowling ball and a feather at the same time, and you got to watch it in slow motion. I will see if I can find that and post that in Classroom so you can watch that, just because it is cool to see. I mean, theoretically, you know that. Like, yes, I've been told this. Yes, I've seen, like, oh, two balls at the same or at different weights dropped. But to see a bowling ball and a feather fall at the exact same speed is cool. So I will post that for you because that is awesome. So acceleration is due to gravity. The velocity is going to be the derivative of the position, and then the position is going to be the position. Acceleration is going to be the second derivative. So we're going to have to find the antiderivatives to get back to velocity and position. And with that, we have initial conditions. The initial condition for velocity, it'll start out at u of 0 and v of 0. And the initial condition for the position will be x of 0 and y of 0. So if we are going to take the antiderivative of a of t, so v of t equals the antiderivative of a of t dt, which will equal the 0 will just become a t plus c, but we'll put the c on the end, and the negative g will become negative g of t plus, we have c1, c2, and so we can put our initial condition when t equals 0, we should get u of 0, v of 0. Usually those will be numbers. That'll be 0, comma 0 plus c. So c is going to be u of 0, v of 0. We can plug that in to get v of t equals t plus u of 0, comma, negative gt, oh wait, that's not t, that's a c. That's a c, not a t, because the antiderivative of 0 is a constant. And so that constant is just u of 0. So we have u of 0, comma, negative g of t plus v of 0. I don't think I can erase just that little bit. Oh, maybe I can. All right, so we have u of 0, comma, negative g of t plus v of 0. That would be with the initial velocities. And then we could take the antiderivative of that to get the position. R of t will equal the antiderivative of v of t dt, which now we have a constant, u of 0. So we'll have u of 0 times t, comma, the negative g of t, the t becomes t squared, divided by the new exponent. So we get negative 1/2 g of t squared plus v naught of t, and then plus c. If we plug in 0, we'll get x of 0, y of 0. So we have x of 0, comma, y of 0 will equal, let's see, if t is 0, that's going to be 0, comma, t is 0, that's also 0, plus c, so c equals x0, y0. We can plug that back in to our equation to get r of t will equal u of 0 t. I always want to say u naught, which is pretty close, plus the initial starting point, x of 0, comma, we have negative 1/2 g t squared plus v of 0 t plus y of 0. And that's our position function. So we have velocity and position functions, which we took just by finding the antiderivatives with some very generic initial conditions. So we can have the summary of what we just did. So you can see that we get the same equations, and we can use it to solve some problems. So we have something like the flight of a baseball. So we have a ball is hit from 3 feet above home plate with an initial velocity of 80, 80. Neglect all forces other than gravity. So we can do that. And so we have our initial velocity, our initial starting point, x of 0, comma, y of 0, is going to equal, it's 3 feet above home plate. We'll count home plate as 0. So we have 0, comma, 3. And we're looking at feet per second, so we'll use the 32 for gravity instead of the 9.8. And so we have find the position and velocity of the ball between the time it's hit and the time it first hits the ground. Because after it hits the ground, obviously the function is going to change significantly. And so we have the equations. We can just plug it into the equations. So our velocity, v of t, was the initial velocity, which was 80, comma, and then negative gt plus the initial velocity, so negative 32t plus 80, which you could go through the steps if you don't remember it. Really the difference between regular physics and calculus-based physics is that in calculus-based physics you can find the equations. In regular physics you have to memorize the equations. So here we could start from the same exact place we did and do the antiderivatives. We have 80, 80 to plug in now instead of just u of 0 and v of 0. So we just get actual numbers. Or if you remember the equation because we just found it, I'd plug them in. And so then the r of t is going to be 80t plus 0, comma. We have 1/2 of this, so negative 16t squared plus 80t plus 3. And so we have that. Did I remember the equation right off the bat? Possibly not, but taking the antiderivative of these constant linear equations on the fly is not too hard as well, especially when you know that you just plug in the initial condition at the end. Show that the trajectory of the ball is a segment of a parabola. So, well, it looks kind of parabola-y. The y value is a parabola, the x value is constant. But to show this, we see x equals 80t, which means that t equals x over 80. We can plug that in over here. We'll get y is negative 16 x over 80 squared plus 80 times x over 80 plus 3 x over 80 squared. That's going to be y equals negative 16 x squared over 80 squared plus 80 over 80, that's just x, plus 3. This is a parabola because we have x squared plus x plus a constant. We could simplify the negative 16 over 80 squared if we really wanted to. That's going to be negative 2 over 800, which would be negative 1 over 400. But in the just figuring out that, hey, this is part of a parabola, we don't actually have to simplify that. And then, assuming a flat playing field, how far does the ball travel horizontally? Plot the trajectory of the ball. So how far does it travel horizontally? Well, we actually have an equation for it, a normal equation. We could use that. Or we could go back to the ones that are a little bit easier because they don't have the 80 squared and stuff. How far does it travel horizontally? Well, we want to figure out when does the y value equal 0. So we can set that to equal 0. Negative 16t squared plus 80t plus 3 equals 0. And we can solve for that. We would end up using the quadratic formula, and we find that t is going to be about negative 0.037 and 5.037. The negative 0.037 obviously doesn't make sense in the problem because you hit it at 0. That negative would be if the ball went from your back to negative time to hit the ground. Yeah, it doesn't make sense. But the 5.037 is going to be how long it's in the air. Plug that into the x equation. So we have x of 5.037 is going to be 80 times that number, which is about 403 feet. And so we found the time it took to hit the ground, and then plug that into x to see how far did it go. For the next part, what is the maximum height of the ball? Well, the maximum height will be when its vertical velocity equals 0, because that's going to be when it changes from going to positive to coming back down, going negative. So the vertical velocity, we can look at the negative 32t plus 80. We need negative 32t plus 80 to equal 0, which means 80 equals 32t, divide by 32. and t equals 80 is 8 times 10, 32 is 8 times 4, so that's 10 over 4, so that's 2.5 seconds. So at 2.5 seconds, it will hit its maximum height. We can then plug that into the position equation for y of 2.5. So that would be 2.5 squared times negative 16 plus 80 times 2.5 plus 3. We do that and we get it's going to be at about 103 feet. So we can plug that into the position equation, do the calculations. You guys can do the calculations. You don't need to see that. And it gets to 103 feet. And then, does the ball clear a 20-foot fence that is 380 feet from home plate, which is directly under the path of the ball? So, what would we do for this? For this, we want to know the vertical height has to be more than 20 when it's 380 feet away. So the x distance has to be 380. It goes 403, so that's useful. So we need to figure out what is the time that hits. We could do it the other way as well, but that's going to be a bit trickier. So let's see, purple. I haven't used red in a while. We'll go red. We're going to set the distance equal to 380. So we'll have the distance is just 80t equals 380 divided by 80. So that means that t equals 38 divided by 8, 19 over 4, which is about 4.75 seconds. Plug that into the vertical one, y of 4.75. So we'll go negative 16 times 4.75 squared plus 80 times 4.75 plus 3. And we get that at that point in time, it's at 22 feet off the ground. So the question is, does it clear the 20-foot fence? Yes. Clears it by 2 feet. And so there's a whole bunch of different kinds of questions we can answer from that. And really, we've answered most of those types of questions even as far back as Algebra 2. There are Algebra 2 questions like that. They're a bit tougher to answer, though, because trying to use this equation to answer those, and that's all you have, it gets a bit trickier. So using the vector equations, the vector components, the velocity, and the distance, and being able to go back and forth between them is hugely beneficial in trying to answer a lot of these types of questions. Nope, same one in case I need extra space. And then range, maximum height, and time of flight. So the range is how far is it going to go. We already saw how to find that, but it's another method because this would be in the general case. In this case, we're going to hit it with an initial velocity of v naught and at an angle of alpha. So before we had the velocity was 80, and so the angle, being that the velocity was the same for both of them, the angle would be a 45-degree angle. Well, it doesn't have to be 45 degrees. It could be any angle we want. So it's going to be an angle of alpha and a velocity, very generic velocity. So we'll be able to find the range. That's the x distance. The time of flight, how long until it hits again. and then the maximum height. So we can get equations for these. And we can plug it in, we can solve the equations using these values. It'll show you in the book, but really what we get is the time of flight, t, that'll be the maximum time, so time will go from 0 to capital T, is going to be 2 times the magnitude of the initial velocity, sine alpha, over gravity. The range, how far does it go, will be the magnitude squared, sine of 2 alpha, over gravity. And then the maximum height will happen at t over 2, and that's going to be v naught, the magnitude of v times sine alpha squared over 2 times the gravity. And here, our initial point will be at the origin. In the last question, our initial point was at, it was 0, 3. So these are going to start at 0, 0. If you want the height, you would just add 3, but the time, the halfway point doesn't quite work as far as t. So a problem like this, we can hit a golf ball. A golf ball will start basically on the ground. So a golf ball is driven down a horizontal fairway with an initial speed of 5 meters per second at an initial angle of 25 degrees from a tee with negligible height, which means it's just sitting on the grass for all intents and purposes. And neglect all forces except gravity and assume the ball's trajectory lies in a plane. And again, we ignore all the forces except for gravity, because if we don't ignore them, Disney's going to buy them and ruin them. So just ignore them. So how far does the ball travel horizontally, and when does it land? So we're just going to plug it in. The horizontal would be the range. So the range is going to equal the magnitude of v naught. Or actually, v naught is an initial speed. So it's speed, 55 meters per second. So notice we're using meters per second, so gravity will be 9.8. So we have that squared times sine of 2 times 25, so sine of 50 degrees, over gravity, which will be 9.8. And we just calculate this. This is going to be a calculator type question because the sine of 50 is not pleasant. Neither particularly is 55 squared. And so we can plug it in. 55 squared times sine of 50 divided by 9.8 is going to get us about 236 meters. And then when does it land? That's going to be the time of flight. So t will equal 2 times 55 sine of 25 degrees over gravity again. So these are just solved for all these various variables. But we can plug those in, and the time of flight, it'll be 4.744 seconds. Then what is the maximum height? That's going to be the y of halfway. So we would just plug the 1/2 of this into the y equation. We don't even have the y equation. We could find the y equation if we wanted to, but we don't need to. But it would be 55 sine of 25 degrees squared over 2g. And so we can plug those in, and we get, it'll be 27.566 meters. And then at what angle should the ball be hit to reach a green that is 300 meters from the tee? So we want the range to be 300. So we're still going to hit it at the same speed. So we're going to have I'll switch colors here. We're going to have 300 will equal 55 squared sine of 2 alpha over 9.8. We're going to multiply by 9.8. So we're going to get 300 times 9.8 will equal 55 squared times the sine of 2 alpha. Divide by the 55 squared. So we get 300 times 9.8 divided by 55 squared equals sine of 2 alpha. And this number, this 300 times 9.8 divided by 55 squared, should be in between -1 and +1, because sine values are always in between that. If you get a value that's not in between that, it means that you cannot hit it that distance at that speed, no matter what the angle is. You'd have to increase your speed. A shot put is kind of like this. That ideal angle, like what angle do you want? Then increasing your speed will get it out, because for a certain speed, you have a maximum angle, and that's it. And the maximum angle should stay the maximum angle no matter what the speed is. So you shot putters out there in the audience might want to think about this and then adjust so that your shot put is always at that same angle when you release it, when you put it, when you shot it. I don't know the verbiage for that, but you can use math to help you in sports. Don't tell anyone though. Anyway, so we get this 300 times 9.8 divided by 55 squared, which is just a number. And then we can take the inverse sine of that number. So we'll go over here. So 2 alpha will be the inverse sine of this crazy 300 times 9.8 over 55 squared number, which, if we do that, is going to be about 0.972. So we're going to go the inverse sine of 0.972 and then divide that by 2. So alpha will equal 1/2 of this inverse sine of 0.972, which means that alpha will be at either about 38.205 degrees or 51.795 degrees, because what'll happen is you could have, if you want to get it here, it could go up and down, or it could go lower, where if you go in the middle, it's going to go further. And so if you take the longest way you could do it, and you either increase or decrease the angle, it'll get shorter, because either it's going to lose some of its momentum and speed into the vertical direction, so it won't go as far horizontal, or it'll have more horizontal speed, however, it won't have the time in the air to go far enough to make it that distance. So it'll get shorter. So a lot of times you will have two angles that will get you to a certain place, unless it's that maximum distance, and there's only one angle that will get you there. So that is the last topic. All sorts of crazy stuff. But again, it's stuff that we've been doing for years. We're just looking at it a slightly different way, which, believe it or not, will make it easier, and it will allow us to get into more complicated problems of this type. Not this year, but in the future. So, with that, always keep working problems, always keep asking questions, and, as always, happy mathing.